Good morning. This is our 13th lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture, we completed our discussion on one-dimensional flow with heat addition, which is also known as Rayleigh flow. And particularly, we tried to analyze the Rayleigh curve from the perspectives of supersonic and subsonic flows by taking the help of property diagrams. After that, now we will start our discussion with one-dimensional flow involving friction. So, typically, like heat addition is having certain effect on the characteristics of the flow that say during our say entry point and exit point, if heat transfer is taking place, it changes the properties of the fluid. Similarly, friction also basically changes the thermodynamic properties of the fluid. So here we will be particularly talking about 1D flow involving friction, and this is also known as Fanno line flow. So like 1D flow with heat addition is known as Rayleigh flow. So this particular situation where we are having one dimensional flow involving friction, this is also called as Fanno line flow. Okay. So basically this problem is very generic, because in all the fluids there is presence of friction, because all the fluids are having some viscosity, and because of the viscosity there will be actually presence of friction. Typically I can represent with the help of a simple case. Say this is my free stream which is moving at velocity v infinity. If I have some solid object over here which is ahead of the flow, I will be finding that immediately whatever layer which will be adhering to the solid object, that will immediately get the velocity of the solid object. And as solid object is stationary, so it means this immediate vicinity fluid particle will also get zero velocity, and this is particularly depicted as no slip condition also. And this particular layer will tries to slow down its next immediate layer, because of which it will be having some velocity but lesser than v infinity, and this will keep on progressing, and finally we will be finding we will reach a situation where our velocity becomes identical to nothing but the free stream velocity. Okay, so after this we will not be having any presence of felt for this particular solid object, whereas up to this section we are having nothing but change in basically the velocity of the fluid medium. Okay, and ultimately this change in velocity is seen only with changes in temperature if we consider the incompressible flow situation. However, for the compressible flow situations there can be significant changes in other thermodynamic properties as well. And the immediate requirement for understanding this type of situation is that if we have a natural gas pipeline, so in a natural gas pipeline I will be having the gaseous fuel, which is actually here I will be having some gaseous fuel which is actually flowing inside this say pipeline. So we will be finding that length of this pipeline will be of the order of say hundreds, or I can say even thousands of kilometers. Okay, so this will be the order of this pipeline. So say if this is my entry point, and say this is my exit point which is after thousands of kilometers, then in between this we will be having, because of the viscosity of this gaseous fluid, I will be experiencing over here some wall shear stress at the surface of this pipe, and this wall shear stress will make certain changes in our thermodynamic properties, and obviously when the length of the pipeline is very large, then changes in thermodynamic properties will also be significant. So this is where we see actually the application of one dimensional flow involving friction. Now let's try to understand this particular situation. So what we will do, we will consider over here a circular pipeline. Say this is my circular pipe, and this pipe is having diameter d and it is having length L. Okay, so this is the pipeline. Now in this pipe, if I consider a small element of this pipe, so say this is one small element of this pipe, and this particular element is having thickness nothing but dx. So dx is the thickness of this particular element over here. Okay, so what I will do now, I will consider that if I have some station 1 over here at the pipe, at the station 1 my density is rho1, velocity is v1, pressure is p1, temperature is T1, say enthalpy is h1, and Mach number is say m1. So similarly I will be having at the exit of the pipe station 2, and where I will be having properties say rho2, v2, p2, T2, H2 and M2, and this is quite evident that these properties at station 2 will be different than the property values at station 1. Okay, now what will happen that in this pipe I will be finding that particularly here we will be having some wall shear stress tau W. Okay, so when the fluid will be moving from left to right, it will be experiencing some shear stress tau at the wall of this particular pipeline. Okay, so that is I am representing as tau W. Another important point which I want to clarify over here is, if you consider flow through a pipe, you will be seeing that once the flow is developed, after that our velocity profile is something like this. Okay, so velocity is not uniform along the entire cross section, but it is having some parabolic shape. Okay, if flow is laminar, if it is turbulent, then actually profile will be different, logarithmic. Now what I want to do over here in this present study, we want to actually take as that I have given the section heading 1D flow involving friction. So in the section title itself I am telling we have to study one dimensional flow with friction. So what we want to do is that this is the variation of the velocity, and what we will do, if I consider corresponding to this the average velocity, so average velocity will be something like this. Okay, so this will be my average velocity. In actual practice I will be having some different velocity profile. It means variation of the velocity along the radius of the pipe. However, what I am doing over here, because we have to make this situation one dimensional. Okay, if I consider the variation of velocity along the radial direction also, then my situation is not one dimensional, because I am having changes along the length of the pipe as well as along the radius of the pipe. Okay, but what we want to do, we want to analyze this situation by considering the assumption of one dimensional flow. So what I am considering is that in place of this type of velocity profile, I will try to have only a average velocity at each and every cross section. So what I am doing basically, I am studying only the effect on the average velocity. So the meaning of average velocity is to mimic this complete flow, how much average velocity is how much velocity is required to the entire cross section, that we are calling it as actually a average velocity over here. Okay, so that this should be very clear. So we are referring over here nothing but this parameter, this type of velocity profile, not this type of velocity profile. Okay, we are considering the average velocity profile over here. Okay, so now we have this situation known to us. Let's now try to see the different governing equations for this type of situation. So first is our continuity equation. As per continuity equation, rho1 v1 is equal to rho2 into v2. and then I have my momentum equation which tells that P1 plus. Okay, now let me write down this momentum equation first using the integral form, because I have now involvement of the shear stress also. Okay, so if I have to take the momentum equation, then what I can do first I will write the integral form of the momentum equation. So as per the integral form of the momentum equation, I have surface integral of rho v vector dot ds vector, and then because I want to write this momentum equation only along this single direction, say this is my positive x direction, so I want to write this momentum equation only along the x direction because I am considering the situation of 1D flow. So I will take over here nothing but the x component of this multiplied with velocity in x direction. This is my rate of change of momentum, and the assumption which I have invoked over here, in the left hand side there was one temporal term also, so that I have not considered. So it means I have invoked the first assumption of steady flow. So I have steady flow, and this is my momentum equation, left hand side of the momentum equation. In the right hand side of the momentum equation, I have surface integral of P into ds vector, and this also I will calculate along the x direction, and then I will be having now one more surface force. So if you see, earlier whenever we considered the momentum equation, we were not considering the shear stress, but now when we are considering that friction is present, then obviously we have to also consider the shear stress over here. So I am considering my tau w is shear stress at any arbitrary location. So I have to consider over here, say, integration of tau w times ds, and this is ultimately acting in x direction only, so I am not explicitly mentioning over here x. Okay, then we have body force. So let's consider the assumption that body force is negligible over here. So another assumption which I am invoking over here, that is nothing but my body force is negligible. Okay, now if you see this particular equation, I will be finding that, let me write this momentum equation. So in terms of momentum equation, I will get that on the left hand side my velocity vector is like this, which is in x direction, and area vector is like this. Say A is area of this pipe, so area vector is like this for this particular left face. So I will get rho1 times v1 into A, but this v1 into A will be with negative sign because both are having the negative directions, and then I have to consider Vx, and Vx is in the positive x direction, so simply I will be writing it as V1, plus for the right face I have rho 2 and area and velocity, because velocity is pointing outside, area is also pointing outside, so both are in same direction, so I will be having A2 into V2, and Vx will also be V2. Okay, this will be equal to minus of, if I consider P1 and dsx is in the negative direction, so minus of A for the left face, and for the right face I will be getting minus of P2 and area is in positive direction, so A. Okay, and then minus of this tau w into integral ds. So this ds area I can write for tau w as nothing but pi d into dx. So pi d into dx is the small elemental surface area through which shear stress is acting. Okay, because pi d will become circumference and dx is the thickness. So what I can do over here, pi d can come out of integration pi d times, and in place of surface integration, because now only I have involvement of dx, I can make this line integral from 0 to L, 0 to L, because dx is having limits from 0 to L, tau w into dx. Is this point clear? So basically this shear stress is acting nothing but on the outer boundary, so near the outer periphery of, we are considering the wall shear stress. So this is acting on the area across the complete circumference. So for that pi d I have considered, and dx is the elemental length I have considered where shear stress value is tau w, and then this dx is varying from the range 0 to L. Okay, so from here one thing I can do, A over here is nothing but my cross sectional area. Okay, so the value of A I can write as pi by 4 into d square. A is cross sectional area, which is pi by 4 into d square. So what I will do, I will substitute A equal to pi by 4 d square, and I will throughout this equation divide by A. If I do so, what I will get minus rho 1 v1 square plus rho 2 v2 square equal to p1 minus p2 and minus of, I have pi d and divided by pi d square by 4. So 1d will be cancelling in the numerator, and d in numerator will cancel, and 1d in denominator will cancel, pi will also cancel. So I will get minus 4 by d integral 0 to L tau w into dx. Okay, so this is something which I am getting, or say if I have to simply write, so I can write that my 4 by, okay, let it be like this only first. So I can write this as rho 2 v2 square minus rho 1 v1 square, okay, and plus p2 minus p1. So I have taken everything on the left hand side, and in the right hand side I have kept the term minus 4 by d integral 0 to L tau w into dx. Okay, now it is important to mention that wall shear stress is nothing but a function of x. Okay, so it's not constant at each and every location of the pipe. So when you will be shifting from left to right, the value of wall shear stress will keep on changing. Okay, so as wall shear stress is a function of x, if we have to perform this integration, I should know this functional relationship. Okay, so what I will do, say initially I will consider that this functional relationship is, say, not known to me. So what I will do, in place of applying, so till now whatever the equation I have got, this equation is applicable for the entire pipe from station 1 to station 2. Now in place of using this from station 1 to station 2, I will try to consider it only for a small element. So what I will do, I will consider only a small element of thickness dx, and this element is so small that at this element our value of wall shear stress is known, that is constant. Okay, so tau w is actually not changing across the thickness of this element. Okay, so tau w, I have taken the shear stress over here for this particular element. Now one important point, p2 minus p1 was the pressure change for the entire pipe length. Okay, now let's consider for this small element our pressure change is nothing but dp. Okay, small dp. Similarly, rho 2 v2 square minus rho 1 v1 square was the total change of momentum. Okay, so this change of momentum I can write as d times of rho v square. Okay, so now for this small element, the same equation will become d times of rho v square plus dp equal to minus 4 by d, and this integration I can remove, I can simply write over here tau w into dx. Okay, now let's try to further take out this first term, and we will write it in some different way. So this first term I can write as d of rho v times v. So this will become derivative of u into v. So derivative of u into v will form d of rho v into v plus v of plus rho v of dv. Now just now we have seen that from the continuity equation rho 1 v1 is equal to rho 2 v2. The meaning of this is that for this particular pipe, product of rho into v is equal to constant. If this is constant, so d of rho v will become 0. So d of rho v square I can write as nothing but rho v times dv. Okay, so if I substitute this, my equation will become d times rho v times dv rho v times dv plus dp equal to minus 4 by d tau w into dx. Okay, so now the beauty of this equation is that at this moment this equation is applicable, this momentum equation is applicable for any type of fluid that is involving friction. Okay, because till now we have not given any assumption of a special type of fluid, because shear stress is also a generalized term. So if I substitute this for Newtonian fluid, then this equation will be applicable only for a Newtonian fluid. Okay, now with this particular equation, let's now further try to deduce this equation for a case of nothing but a for the case of a calorically perfect gas. Okay, so we are here over dealing with nothing but the compressible flows. Okay, so in compressible flows we will find that majorly this situation will come with the gases only. Okay, and the easiest way for analyzing gases is to consider gases as nothing but the calorically perfect gas. Okay, so now let's invoke the assumption of calorically perfect gas. So if I consider calorically perfect gas, and then I will be getting some assumptions. First is PV equal to RT. Okay, or in other sense I can also write P is equal to rho RT. And another important point is I will get that my speed of sound is nothing but equal to square root of gamma RT, which can also be written as gamma P by rho. Okay, so let's now invoke these equations into our main equation, and let's try to reduce it for a calorically perfect gas. Okay, so from here what I will get, my equation is rho v dv plus dp equal to minus 4 by d tau w into dx. Okay, now whenever you have studied your fluid mechanics, you might be remembering we write wall shear stress as nothing but tau w is equal to F times half rho v square. Okay, where this parameter F is considered as nothing but a friction factor. Is this point clear? So do you remember from your basic fluid mechanics, we have tau w is equal to F times half rho v square, and even you will be surprised, in some places you also use tau w is equal to 4F times into half rho v square. Okay, sometimes we use F, sometimes we use say 4F notation. So basically, in order to keep the magnitude same, this particular F has to be equal to 4F in this situation. Okay, so the simple difference is there. When I write this expression 4F, During that time, I call this F as nothing but my Fanning friction factor. Okay, and when I simply write tau W equal to F into half rho V square, then I call this F as nothing but my, then I call F as Darcy friction factor. Okay, so this is you have to make a clear distinction. For example, whenever we calculate the Fanning friction factor for a circular pipe, its value comes out to be 16, and when you its value comes out to be as 16, and when you represent it, the internal pipe flow in terms of the, say its value comes out to be 16 by Reynolds number. When you represent it in terms of the Darcy friction factor, then say for a pipe we say for fully developed laminar flow, friction factor is equal to 64 by Reynolds number. So you have to make the distinction over here. Okay, so if you are making this assumption tau W is equal to 4f times half rho V square, then whatever f we are considering in our formulation, that is nothing but a Fanning friction factor. Okay, and if we are considering tau W equal to f half rho V square, then we get a Darcy friction factor. And you also know that we have one important diagram to calculate the value of friction, which is known as friction factor, which is known as Moody's diagram. Okay, so as per the Moody's diagram, we represent Darcy friction factor along abscissa and Reynolds number along ordinate. Then I will be having for laminar flow situation something like this, and after this point for turbulent flow I will be finding that I will be having over here multiple lines, and here in these multiple lines, these lines are nothing but for the different values of relative roughness. So this will be epsilon is absolute roughness. If it is divided by hydraulic diameter of the duct, then we call it as nothing but relative roughness. And this important diagram is known as Moody's diagram, and Moody's diagram gives us nothing but the Darcy friction factor. Is this point clear? So you have to make clear distinction between the Darcy friction factor and the Fanning friction factor, but it is very clear that friction factor is nothing but a function of Reynolds number and the relative roughness. So relative roughness is epsilon absolute roughness divided by dH. Okay. For laminar flow, it's a sole function of Reynolds number, and for turbulent flow, it also depends upon epsilon by on the roughness of the pipe. Okay. Okay, so with this assumption, what we will do now, in our momentum equation, I will replace it with tau W equal to F half rho V square. Okay, so I am considering over here the Darcy friction factor. Okay, so if I consider Darcy friction factor, I can write rho V dV plus dP equal to minus 4 by d into F times half rho V square into dx. Okay. Now let's do one more thing. Let's divide this complete equation. Let's divide this complete equation by pressure. If I divide this equation by pressure, I will get rho V dV by P plus dP by P equal to minus 4F dx by d times half of rho V square by P. Okay. Up to this point, is it clear? Now what I will do, I will multiply this first term, multiply and divide with gamma by gamma. Okay, so I have multiplied and divided gamma by gamma, and same thing I will do with the last term on the right hand side. Okay, so that is, here also I am doing gamma by gamma. Okay, so this gamma P by rho has become nothing but my a square. Okay, so from here I will get gamma v dv by a square plus dp by p equal to minus 4f dx by d times half of gamma v square by a square. Okay, now what I will do, because if I see the first term of this equation, in the denominator I have a square and in the numerator I have only v. So what I will do, I will here multiply and divide with v. So if I multiply and divide with v, in the numerator also I get v square. V square by a square will become nothing but the Mach number. So from here I will get gamma Mach number square into dv by v. 1v is there in the denominator, plus dp by p equal to minus 4f dx by d, and here I will get half gamma Mach number square. Okay, so this is important finding. So from here you see, whenever I am substituting a equal to gamma p by rho, then I have nothing but invoke the assumption of an perfect gas. Okay, okay. Let's now try to see how I can write this dv by dv and tp by p in terms of actually Mach numbers. Okay, so another interesting point is that I know that my velocity, flow velocity, can be written as Mach number times A. Is this point clear? And A I can write square root of gamma RT. Now let's take log of this particular equation. So if I take log of this equation, then ln of V will become ln of M plus 1 by 2 ln of gamma R I have kept together plus 1 by 2 ln of t. Is this clear up to this point? Now let me take the derivative of this ln V ln M. So if I take differential of this will become derivative of ln V will 1 by V into dV equal to 1 by M into dm plus 1 by 2 gamma R into d of gamma R plus 1 by 2 t into d of t. Okay, now interestingly, this value of 1 by this d of gamma R will be equal to 0. Why? Because gamma for a calorically perfect gas, Cp and Cv are constant. These are not the function of temperature. So ratio of Cp by Cv will also be constant, and R is always a constant quantity, characteristic gas constant. So from here I can simply say that dV by V I can replace with dm by m plus 1 by 2 dt by t. Okay, so what I will do now, let me name this equation in the previous slide as equation number 1 and say this is my equation number 2, where I have actually calculated dV by V. Okay, let me now also try to calculate dP by P also. So we have seen that from continuity equation rho into V is equal to constant. Using the ideal gas assumption, I can write rho as nothing but P divided by RT, and in place of V I can write simply Mach number into square root of gamma RT. Okay, and this is nothing but a constant quantity. So from here I will get that P into M, and this will become square root of gamma divided by square root of RT equal to constant. Okay. Now let me take log over here. So I will get ln of P plus ln of M plus 1 by 2 ln of gamma minus 1 by 2 ln of R minus 1 by 2 ln of T, and this will be equal to ln of constant. Is this point clear? So now if I take the differentiation of this, I will get dp by p, ln p will be 1 by p in dp by p plus dm by m, and 1 by 2 ln of gamma will be 0 because gamma is constant, r is constant, this will be 0, minus 1 by 2 dt by t, and in the right hand side also I have ln of constant, so that will be equal to 0. Okay, so from here what I will get, dp by p equal to minus dm by m plus 1 by 2 dt by t. Okay, so let me number this equation as equation number 3. Now what I will do, I will substitute equations 2 and 3 in equation number 1. So what I will get, gamma m square times what I have dv by v is dm by m plus half dt by t. Okay, and then I have dp by p. So dp by p will become minus dm by m plus half dt by t. Okay, is this one clear? And that has to be equal to minus 4f dx by d into half gamma m square. Okay, this is correct. Now what I can do, this term half gamma m square, I can actually take this on the left hand side. So if I do so, I will get 2 by gamma m square, okay, in the left hand side multiplied with each and every term. So here gamma m square will cancel out, so I will get 2 times of dm by m plus 1 by 2 dt by t minus of dm by, here what I will get, minus of 2 dm by gamma m square, correct, plus 1 by gamma m square into dt by t. Up to this point, is it clear? Okay, here 1 m is already there, and yes, so this will become gamma m cube. 2 times dm by dm plus half of dt by dt minus 2 dm by gamma m cube plus half gamma m square dt by dt, and this will be equal to minus 4f dx by d. And simply what I can do, I can take minus sign also on the left hand side, so I will get 4f dx by d as nothing but minus 2 dm by m, and this will also become minus, and 2 will cancel out, minus of dt by t plus 2 by gamma dm by m cube minus 1 by gamma m square into dt by t. Okay, up to this point is it clear? Now everything we have written in terms of Mach number, but only the parameter we are having in extra is dt by t. So this we can deduce with the help of energy equation. So if I let me number this equation as 4, and in between I will do some take help of energy equation to calculate dt by t. Okay, so if I take the help of energy equation, what I will get, h1 plus, for flow with friction, h1 plus v1 square by 2 will be equal to h2 plus, why? Because we don't have any heat addition over here. Okay, neither we are adding any heat nor we are removing any heat. So from here simply I can say that h plus v square by 2 equal to constant. What is h plus v square by 2? This is nothing but h naught, static enthalpy. Okay, sorry, stagnation enthalpy, total enthalpy or stagnation enthalpy. Another important point is, from the concept of calorically perfect gas, I can write H equal to Cp times T. So from here I can also write Cp times T plus V square by 2 equal to constant, which will become Cp times of T naught equal to constant, and simply I can say that T naught will also be equal to constant. Okay, so stagnation temperature also for 1D flow with friction will be nothing but constant. That is what we are inferring from the energy equation. Okay, so now what I can do, if my T naught is equal to constant, I have the relationship between T naught and T, and the relationship is T naught by T equal to, we have calculated earlier in terms of Mach number, 1 plus gamma minus 1 by 2 into Mach number square. Okay, so that is something which we have calculated earlier. So from here I can write T naught will be equal to T times 1 plus gamma minus 1 by 2 m square. If I take the log, so ln of T naught will be equal to ln of T plus ln of 1 plus gamma minus 1 by 2 m square, and if I take now the differential, then this will be 1 by T naught into D. T naught will be equal to dt by T plus d of 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square. Okay, now this will be equal to 0 because stagnation temperature is constant. So from here I will get that dt by t equal to minus of d 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square. Say this is my equation number 5. Okay, let me now substitute equation 5 into equation number 4. Okay, so if I substitute 5 into 4, I will get 4f dx by d equal to minus 2 dm by m and then I have one term dt by t with minus sign. Okay, and dt by d I have this with minus sign, so minus minus will become plus, so I will get plus d of 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square. Okay, Then I have the next term plus 2 by gamma dm by m cube. So plus 2 by gamma dm by m cube, and then I have minus 1 by gamma m square dt by dt. So here minus minus will become plus. So I will get plus, let me write it in the next line, plus 1 by gamma 1 by gamma m square into d of 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square. Okay. Now from another point, what I can do in the first term, so if say I have m square, okay, if I have to calculate d of m square, then I can write d of m square as nothing but equal to 2 times m into dm. Is this point clear? So 2 times m into dm I can replace with d m square. So what I will do in the first term, I will multiply with m and divide with m. So if I multiply and divide with m, then 2m dm I can replace with d m square, and in the denominator I will be having m square. Okay, this operation I am doing just to facilitate the integration and then finally have easy expression for the estimation of say effect of friction. Okay. Okay, so if I invoke this assumption, then I will get this mathematical manipulation, then I will get 4f dx by d equal to minus of d m square divided by m square plus d of 1 plus gamma minus 1 by 2 m square plus 2 by gamma into dm by m cube and plus 1 by gamma m square into d of 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square. Okay. So now let me number this equation as equation number 6. Okay. The reason why I am doing so, because if you see now, the first term of this equation can be integrated, second term can be integrated, third can be integrated, but in the last term still actually it is not in the direct form which we can actually integrate. Okay. So what we will do now, we will try to find out the more simplified form for the last term of this equation. Okay. So for the last term, what I will get now, let me see, 1 by gamma m square times 1 by 1 plus gamma minus 1 by 2 into m square. So let me try to write this in the simplified form. Okay. So this I can write as nothing but the in terms of C1 divided by gamma m square plus C2 divided by 1 plus gamma minus 1 by 2 m square. Okay. So this is how I can write it. Up to this point, is it clear? So I have factored it in the form of C1 by gamma m square plus C2 by 1 plus gamma minus 1 by m square. Now what I have to do, I have to find out the values of C1 and C2. So in order to find out the values of C1 and C2, let's take first LCM on the right hand side. Okay. So then what I will get, okay, here only let me write, I will get C1 times 1, this 1 will get multiplied, plus C1 times gamma minus 1 by 2 m square plus C2 times gamma m square divided by gamma m square and then 1 plus gamma minus 1 by 2 m square. Okay. Now if you compare this last term with the extreme left, denominators are same, so denominators will be cancelling out, and in the numerator I am finding on the left hand side I have only a constant quantity 1, and whereas in the right hand side I have C1 as a constant quantity, then C1 is also, C1 and C2 are also involved with m square. Okay, so if you compare in the left hand side, I don't have any, I have only a single constant, that is 1. So I can equate this first constant on the right hand side and constant on the left hand side. This will give me C1 is equal to 1. Is this point clear? And if I compare the second term involved C1 into gamma minus 1 by 2, and that is multiplied with variable m square, and then plus C2 gamma is constant, that is multiplied with variable m square, and I don't have any term involving m square on the left hand side. So all the coefficients of m square on the right hand side I can just equate equal to 0. Okay, so from here I will get C1 times gamma minus 1 by 2 plus C2 times gamma equal to 0. So C1 is already 1, we know about it, so C1 is already 1, so I can get from here C2 will be equal to minus of gamma minus 1 by 2 and divided by gamma. Is this point clear? So we have got the values of C1 and C2. So C1 is 1 and C2 is minus of gamma minus 1 by 2 gamma. Okay. So now let's substitute this last term in the form of C1 by gamma m square, C2 by 1 plus gamma minus 1 by 2 m square in equation number 6. So if I do so, my equation number 6 will become 4f dx by d this will be equal to minus of dm square by m square plus d of 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square plus 2 by gamma dm by m cube, and then I have actually plus. Now what I will do, in place of this entire term I can write C1 by gamma m square. So C1 is 1, so plus 1 by gamma m square, and then but this derivative has to multiply it with both the terms. Okay, because we have replaced over here only this quantity. We have replaced this quantity with C1 by gamma m square plus C2 by 1 plus gamma minus 1 by 2 m square, but this derivative has to multiply. Okay, so if I take d of 1, that will be 0, gamma minus 1 by 2 will be constant. Is this point clear? Gamma minus 1 by 2 will be constant, and this will become d of m square. So here I will get 1 by gamma m square into gamma minus 1 divided by 2 and d of m square. Is this point clear? Then I have, after this what I have? I have C2 divided by 1 plus gamma minus 1 by 2 m square. So C2 is nothing but my, what is the value of C2? So I will get minus of gamma minus 1 upon 2 gamma into d of 1 plus gamma minus 1 by 2 into m square divided by 1 plus gamma minus 1 by 2 into m square. Is this point clear? Up to this point, is it correct? Is it fine? Now if you see this first term, dm square by m square, here also I am having dm square by m square. Okay. So in both the terms, if I take dm square by m square common, coefficient I will get minus 1 plus gamma minus 1 by 2 gamma. Okay. And this will become minus of 2 gamma plus gamma minus 1 by 2 gamma. So if I take minus sign outside, so I will get minus of gamma plus 1 by 2 gamma. Is it clear? What I have done in this dm square by m square, I have taken minus 1 as coefficient out, and here coefficient in dm square by m square, coefficient is gamma minus 1 by 2 gamma. If I do algebraic manipulation, this comes minus of gamma plus 1 by 2 gamma. Okay. So I can write here that 4f dx by d can be equal to minus of gamma plus 1 by 2 gamma times d of m square by m square. Okay. And then this m cube term is actually sole, so plus 2 by gamma dm by m cube. Okay. And then I have one more term over here. Okay. And that particular term is nothing but this. If you see d of 1 plus gamma minus 1 by 2 m square, okay, it is having, and here also I have the same term. So this term is having coefficient 1, this term is having coefficient 1, so 1, and this term is having coefficient gamma minus 1 by 2 gamma with a negative sign. Okay, so minus of gamma minus 1 by 2 gamma, it will become 2 gamma minus gamma plus 1 by 2 gamma, so it will become gamma plus 1 by 2 gamma. Okay, so here I will get plus gamma plus 1 by 2 gamma times d of 1 plus gamma minus 1 by 2 m square divided by, is it clear? This one? Yeah, this is in bracket like this. So this minus is basically with the entire term, not with gamma. Okay, up to this, is it clear? So now if you see, if I have presence of friction in small differential element dx, then I have represented that entire equation in terms of nothing but the Mach number. So here you can see that this can give you the how much is the change in Mach number. Now if I have to find this equation for entire pipe, what I will get? What will be the effect on complete pipe? So for the effect on complete pipe, we have seen that our length of pipe is from 0 to L. So I can write 4f dx by d, and integration of this from 0 to L, this will be equal to integration of entire right hand side from, what will be the limits of integration? Tell me. So right hand side is minus gamma plus 1 by 2 gamma dm square by m square plus 2 by gamma dm by m cube plus gamma plus 1 by 2 gamma into d of 1 plus gamma minus 1 by 2 m square divided by 1 plus gamma minus 1 by 2 m square, and integration of this entire from, limits of integration will be m1 to M2. Okay. Why? Because at x equal to 0 our upstream Mach number is 1 and at x equal to L our downstream Mach number is 2. So this we have to integrate from 1 to 2. So I will get 0 to L 4f dx by d equal to minus gamma plus 1 by 2. Gamma is constant. Okay, so this is a constant quantity. Integration of dm square by m square will be ln of m square. Is this one clear? Ln of m square, and if I substitute from m1 to m2, it will become ln of m2 by m1. Is this one clear? Then plus 2 by gamma, and integration of dm by m cube will be m power minus 3 plus 1 divided by minus 3 plus 1, and limits of integration from m1 to m2. Then I will be having plus gamma plus 1 by 2 gamma into ln of 1 plus gamma minus 1 by 2 m2 square divided by 1 plus gamma minus 1 by 2 m1 square. Okay. And finally what I can do, I can write 4 in place of f. I can write say f bar, okay, average friction factor, times L upon D will be equal to minus of gamma plus 1 by 2 gamma times ln of m2 by m1. This will become minus sign and 2 will cancel. So minus 1 by gamma into this will become 1 by m square. So 1 by m2 square minus 1 by m1 square plus gamma plus 1 by 2 gamma into ln of 1 plus gamma minus 1 by 2 m2 square divided by 1 plus gamma minus 1 by 2 m1 square. Okay. Interestingly, what I am doing, this f bar I am considering as nothing but the average friction factor for the entire length. So it will be length averaged quantity. So I can write f bar as nothing but 1 by L integral 0 to L f of dx. Is this point clear? Is it clear? So what are the physical inferences of this, that I will deal in the next lecture. So mathematically I have explained how the effect of friction can be accounted for to relate Mach number, downstream Mach number, okay, and the upstream Mach number, particularly for a calorically perfect gas. Now what are the physical inferences of this, that I will take up in the next lecture.